In part C, we're asked to use the Lagrange error bound to show that the difference or the error between the actual value of f of 1/10 and the estimated value of the function at 1/10 is less than 1/100th. Well, the Lagrange error says that the absolute value of the function minus the value for the Taylor polynomial, the nth degree Taylor polynomial, has to be less than the absolute value of the n plus first derivative of f evaluated at some value c divided by n plus 1 factorial times x to the n plus 1. And I guess we really are talking absolute values here as well. So we could put the absolute value around the whole expression. So you recall that we're going to evaluate the derivative, the n plus first derivative of f at some value c, where c is between a and x. X in this case is 1/10. And we're told that we're centering around 0, so a is equal to 0. Now you recall that p of x was a third degree Taylor polynomial. So the first unused term would be the fourth. And we've already calculated this above. The fourth derivative of f of x was 5 to the fourth times sine of 5x plus pi over 4. Now what we want to do is we want to make this a maximum value. And sine hits its maximum value at the value of 1. And sine of 5x plus pi over 4 will equal 1. And sine hits its maximum value of 1 when x is equal to pi over 2. And so we can solve for x here by subtracting pi over 4 from both sides, dividing both sides by 5. And when x is equal to pi over 20, since pi is roughly 3, we're working with about 1/7 here, which is a little bit larger than 1/10. So we would like to pick a value between 0 and 1/10, and we came up with 1/7, which is a little bit larger than that. And the way this is going to work is that's going to be fine for us. Since that's easy to calculate and it's not that much difference, we're going to assume that sine of 5x plus pi over 4 in that fourth derivative is just equal to 1. And it happens at 1 over 7 roughly, which is a little bit larger than 1/10, but that's going to be fine for us. It's still setting a boundary, and we'll check at that value to see whether it's enough for our error tolerance. So now we're ready to construct the right side of that inequality. And we know that f to the n plus 1 of c is just 1. And so that simplified our the right side of the inequality a great deal. And we also know that n in this case, or n plus 1 rather, is equal to 4. And I think at this point it's safe to lose the absolute value since our x value is 1/10 is positive to begin with, and we're raising it to the fourth power. So we have 10 to the fourth, which is 10,000, times 4 factorial, which is 24,000. Okay, so I do realize that I left out the 5 to the fourth power, which should be the value of the derivative instead of 1. The sign is 1, but that still leaves 5 to the fourth power. So I fixed that, and now I have to fix it in the other two statements. And I've erased the last statement there. So what this does give me, though, is 625 over 24,000. And there are a number of ways of going about this. And again, you don't have a calculator here, so I would say you could round up to 625, and that would give you 1,000. And that would make it a simple 1 over 240. So it says that our estimate, or the error bound, is less than 1 240th, which is less than 1/100th. So there may be other ways of going about that last part of it, but that's the gist.